Okay, so we have the second half here now of this gravity section, and that means momentum and energy, basically. We talked about forces and kinematics. This is the momentum and energy half. So we're sort of talking about gravitational potential energy and how we might calculate that, and then we'll move into a little bit about momentum. And we'll, by the end of it, we'll get to talking about Kepler's laws, because those are really energy and momentum concepts. So the first thing is, right, this should be familiar for when we talked about energy earlier, right, as a general concept, right? The change in potential energy is what happens if you take the force and integrate it over a distance with a negative sign, right? The negative sign comes from the relationship between work and potential energy, right? This right here is the work done. And then the negative sign turns it into potential energy. So here, all we're going to do is we're going to say, well, our force is gravity, so we can calculate the gravitational potential energy. And so then this is our expression, right? We're integrating the gravitational force along a distance. In this case, right, I've written r and not x because we're moving sort of along a straight line away, radially away from like the center of a circle. So the only thing that's left to do is we have to figure out the ends of our integral to turn this from an indefinite to a definite integral. And that's the same as asking this question, which is, where do we have zero gravitational potential energy? In our old way of approaching gravitational potential energy, MGH, we had zero gravitational potential energy at ground level, whatever we defined that to be. But that doesn't make a whole lot of sense anymore. And so we need to make a new choice for what means zero gravitational potential energy. And the most logical choice, although it's sort of mathematically illogical, the most logical choice conceptually is to say that when there's no interaction, there's no energy. And no interaction happens when r goes to infinity, right? If you're an infinite distance away, you're no longer interacting. And if you're no longer interacting, it doesn't really make sense to talk about the gravitational potential energy being anything other than zero, right? So we're going to call, right, this is r, it's not a good arrow, but I can't erase it, right? R goes to infinity is when we have zero energy. And so if we make that and perform that integral, right, we're integrating really 1 over r squared. And that's going to give us a negative 1 over r, right? And that's what you see in here. And so it's important to note that there's a negative sign in gravitational potential energy, right? Gravitational potential energy is always negative because G, M1, and M2 are always positive, and so is R. R is a distance of separation, not a direction. Okay, so this equation is important to know. You probably don't have to rederive it, but you have to know sort of how you could have derived it, and you have to be able to use it on the AP test. So graphically, right, this is what it looks like, right? U approaches zero as r goes to infinity. That was the definition we said, right? If you're an infinite distance away, there's no potential energy. And as the separation goes to zero, we get increasingly large amounts of energy, more negative. But because r can never be absolutely zero, right? Two objects can't have their centers at the same point. It doesn't matter that that sort of has no limit down in that direction, right? So there's one thing that can be very confusing, and that's communicating changes in potential energy when everything is negative, right? We know, again, from everyday experience, right? If you hold a ball in the air and drop it, it's going to speed up as it travels to Earth, right? That is a decrease in r. A decrease in r in the potential energy, right? Right? If r in the denominator here is getting smaller, the magnitude of u is going to increase, right? R in the denominator getting small means the magnitude of u gets bigger. But because of this negative sign, a bigger negative magnitude means that the value of u, not the absolute value, but the actual value of u has decreased, become more negative. Right? So becoming more negative and decreasing are the same. And so if u has become more negative, that energy that was lost from potential energy has to go somewhere. And so therefore it goes into kinetic energy. That's why it speeds up, right? This graphical interpretation should look familiar, right? The difference between the potential energy and the total energy is always the kinetic energy. As U becomes more negative, then we have space for the potential energy to become something positive. And so conservation of energy still works, but the wording is a little bit tougher because, again, you have to remember, right, this is really the key, right? The magnitude might get larger, but there's a negative sign. That negative sign is very important. So let's do some practice, a couple things here. First thing, right? Notice they've asked very clearly, like bigger absolute value of potential energy. So, right, we know that that's our equation. And so we just look at what we got, right? So this system A, we have 2m times 2m over 2r, capital R. And system B, it's m times m over r. Notice, this in the denominator is not, right? This is not r squared like the force. It's just linear. And so because of that, right, we only cancel one of the factors of 2. And this one doesn't have, the system B doesn't have anything to cancel at all. So system A is going to have twice the total energy, or twice as much negative potential energy. So it should be system A. Right? Don't get the force and the potential energy confused. They are different things. And my slides have gone away, so just a second. That's just the answer anyway, so it's A. Okay, so that's the first type of simple practice one. This one's a little bit more time consuming, right? You're given a description of where masses are and asked about the gravitational potential energy of the system of masses. So the first thing to do is kind of draw this out, right? We have our coordinate system, and we're going to put 3 masses on it. One's at the origin, one is at 3, 0, and one is at 0, 4, roughly, right? So this is 4.5, this is 3, and this is 2.5 kilograms, right? And this length is 4, this length is 3, and so hopefully you can see without using the Pythagorean theorem that that length must be 5, right? A 3, 4, 5 triangle. So when we calculate the potential energy, I'm not going to do every single step here because it's a lot of writing, but the key is that potential energy is every possible interaction. There's an interaction, there's an interaction, and there's an interaction. So the potential energy of the system is U1 plus U2 plus U3. I have to calculate all 3. Right? Each pair of masses is an interaction, so each one has its pair of potential energies. And each one of those U's is G times M over R times -1. And so if you plug that all in very, very carefully, you should get that the answer is, once I find it, C. Right? So you get to do the math, but that's kind of like this sketch and this, right, concept is really all you need. Notice something else I didn't do, right? This is an energy. These are not vectors, right? I just added the numbers. Was working. So maybe, okay. So the next one, right? We have this idea of escape speed, right? This is really an energy conservation question when you see this. So we have a rocket fired away from the surface of the Earth, and we want to escape and never return, right? That means no longer interacting, right? So we know what the potential energy is at the start and end, right? We're at the surface of the Earth, and at the end, right, escape means UG equals 0. It's no longer interacting. And so what we want to do is figure out sort of the kinetic energy necessary to make that condition true, right? If we want to end up with 0 potential energy at the end, we have to have a positive kinetic energy, so we can take the negative initial potential energy, add the positive kinetic energy, and end up with 0 at the end. Right, so this is them kind of explaining that. Here's what it looks like, energy conservation, right? This right here is the surface of Earth. Right? We have a potential energy, notice it's negative, and we want to figure out what is V1. That's our unknown. But when it's escaped, we no longer have potential energy left, but we want the minimum speed. And so that means we have no kinetic energy left either. right? So we can rearrange and solve. And if you do that, you get about 11,000 meters per second, right? The escape speed from Earth. Right? Anything that you launch upward from Earth's surface at any speed above that will never, ever come back. Assuming the Earth's not rotating. If it's rotating, then where you are matters a little bit more. Okay, so a similar question, right? So suppose the Earth stops, right? It's currently moving at a very high speed around the sun. Let's say it stops, and then therefore the sun's gravity will pull it straight in towards the sun. How fast is it going to hit the sun traveling at? This is really an energy conservation question as well. Our initial energy, right, is going to be just the potential energy, right? There's no kinetic energy left. So this is U G sun Earth, which is G times the mass of the Earth times the mass of the sun over R sun Earth with a negative. And right? So then the final energy is two things. Right? Their centers don't hit when the Earth impacts the sun. So there's still potential energy left, but there's also kinetic energy. Right? And this is what we're trying to solve for. But this is GMEM sun over radius of the sun plus radius of the Earth, right? When their edges hit, it's because the radius of the sun and the radius of the Earth is how far their centers are separated. And I'm gonna relabel this. This is right. This is the distance from the sun to the Earth. And if energy is conserved, these two things must be equal, right? So we get G, oops, I forgot a negative sign, GMEM sun over D sun Earth, negative, equals 1/2 MeV squared minus GMEM sun over R sun plus R Earth. Notice one sort of handy thing about this is that you don't need the mass of the Earth, right? That will cancel. The mass of the sun and the distance from the sun to the Earth and the radius of the sun and the radius of the Earth, those are all constants that you would either be given or should look up in your book, right? That table that I had in an earlier slide. So look those up, and then you do some algebra, and if you do it all very, very carefully, you should find that V is roughly 42,000 meters per second, right? Quite fast, which makes sense. The sun has very strong gravity. Okay, so we are asked a question about escape speed on another planet. And since we know that's energy conservation, really what I'm going to do is get what the potential energy is on the surface of those planets, right? If we're starting on the surface of both. So UG Earth is GMEM rocket, whatever that is, over R, negative. And UGX on planet X is GMX MR over RX, right? This is RE. But we know a relationship between the mass of the Earth and the mass of planet X, right? And we also know a relationship for the radius, right? And I see something quite nice here is we have a 1/3 and a 1/3, which cancels. And so now the potential energies on the surface are exactly the same. And so I know if the potential energies on the surface are exactly the same, you need the same amount of kinetic energy to escape, and therefore you need the same speed. So it's got to be A. Okay, so the next thing is to think about, we now have two ways of calculating gravitational potential energy. Just like we did with force, we kind of want to show they're the same thing. I'm not going to talk a huge amount about this because it's really a mathematical thing, but if you've seen in your math classes, which you might not have yet, and if you haven't, it's a really cool thing to kind of look up, this thing called a binomial approximation. And so it's a mathematical statement, not a physics statement, but it comes up a lot in physics, is that if x is very tiny, this quantity 1 plus x to the n can be turned into a much simpler expression, right? It's approximately just 1 plus nx. Okay? And I'm going to show how this is used in just a second, but that's sort of the mathematics behind it. I'm not going to obviously prove that. I think it comes from the Taylor series, if I remember correctly. So if we take the gravitational potential energy, right, this is our new way of writing gravitational potential energy. You notice the only thing I've done is I factored out RE, right? So this is if we are some little height y above the Earth's surface, right? So we're just a tiny bit above the surface of the Earth. So our distance from the center of the Earth is RE plus y. And so if we look at that with the binomial approximation, this thing right here is 1 plus y over RE to the negative 1. But this is really, really, really tiny because we're only a small bit above the Earth's surface. So we can rewrite it as this expression right here in the case that y is really tiny. Like this is every experiment we've done this year. This right here is two terms, right? Which I can rewrite, kind of. Right? So this is a constant. We know that constants don't affect the potential energy at all. So we don't really care about that, right? It's about changes in energy. And this you should recognize from the previous day. This is what we defined as little g. And so this is g my plus a constant. And so that's why we can write near Earth's surface the potential energy as just mgy. So as long as you're close to Earth's surface, you can keep using the old way. If we're not close to Earth's surface, you have to use this new, slightly more complicated thing, right? And that's what this is described right here. Okay, so kind of an example of when this matters. We're trying to launch satellites to about 400 kilometers in the air. And we want to know sort of how fast do we have to launch it to reach a certain speed at that height. We're going to ignore air resistance, but we're going to try this two different ways, both assuming the Earth is flat and the potential energy is mgy, and the new way. This is energy conservation then, right? This is our energy high above Earth's surface, and this is our energy on Earth's surface, right? And we know everything about the final energy because we know how fast we're going and how high we are. And for the initial energy, we're trying to find how fast we're going, right? That's what all this information down here is sort of plugged in up there. So it's kind of ugly algebraically, right? Using this form of potential energy is more algebraic work because you have denominators and things like that, but it's not too much worse. So if you carefully plug all that in, you should get that the correct speed is 2770 meters per second. Now, if we do the same thing using potential energy of mgy, right, this should look very familiar, right? We've done that kind of calculation a lot. If we assume the Earth is flat and calculate it out again, we get a slightly but noticeably different speed, right? A little bit higher, right? Because for using this right here, we're assuming that Fg is constant, which it's not, right? It gets weaker as you get farther from Earth's surface. So by assuming it's constant, we also are then calculating we have to go faster, right? We need more energy we don't really need because the force gets weaker the farther you get. So it's a problem, but notice how it's only 2% wrong, and that's 400 kilometers above Earth's surface. So for most things we do, mgh is a fine potential energy. Okay, so the next thing now is to connect this back to Kepler's laws. That's what satellite orbits and energies are going to be. So the first thing, right, we can use this idea we can use kinematics and forces to calculate this right here, right? This I'm not going to drive fully because it's pretty straightforward. You should be able to do it because it comes from F equals ma. A is v squared over r, and F is G m1 m2 over r squared. If you put all those pieces together, which is what we have, right? This is something moving in a circle under the influence of gravity. You can solve for V and you get that answer. Notice this m is the thing that is orbited. Okay? And so since we now know the speed of something, right, we have a relationship between speed and position. That's going to help us relate kinetic energy and potential energy. So, two satellites, right, a heavy one and a light one. They're orbiting the same distance from Earth's surface, which has a higher speed. Well, to think about this one, we have to remember what I just pointed out, right? This m is the thing being orbited. Does not depend on the satellite mass. So they have to have the same speed, right? The speed you travel at to orbit a planet is dependent only on where you are, nothing else. Right, same speed. So now we have two orbits, right? A close by and a far off. And we want to know about the speed. Well, again, right? If r is small, then v is big because r is in the denominator. So the smaller orbit should be going faster. Right? They didn't have to be identical. Wouldn't change anything. Okay, so this one uses a little bit more information and should start to look like one of Kepler's laws if you maybe recognize it. So again, I'm just going to kind of set it up. So we have here a satellite in a circular orbit, right? That's uniform circular motion, and we know the period. So we can calculate the speed it travels at, right? Is a distance over time, right? Uniform circular motion is no acceleration, so it's okay to use that simple kinematics one. The distance we travel is 2 pi r over the period, right? One circle, one circumference, which is 2 pi r Zeeman plus 230 kilometers, right? That's how far we are from the center, over 89 times 60 seconds, right? We have to work in seconds. So we can calculate how fast we're going. If we know how fast we're going, we can then use gm over r, right? We can rearrange this, right, to solve for our unknown m. And once again, r is this whole thing, right? The distance you are away. And so if you very carefully do all that and get your unit conversions, right, this has to be 10 to the third meters. You need to do unit conversion there. If you do all that very, very carefully, you should get 6 times 10 to the 24th kilograms. Notice that this is a relationship between where you are and the period, right? That's what one of Kepler's laws was. So let's look at that in a little bit more detail. This is another, right, actually before we do that, right, very simple, right? We know the height. If we know the height, we can find the speed. Just plug it in, right? That's the important takeaway message here. If you're in a circular orbit, knowing how far you're away defines the speed exactly. So, okay, Kepler's third law, right? This was the one that was really mathematical and confusing. The square of the period is related to the cube of the semi-major axis length, or in this case, the radius. So we kind of did that in the previous problem, right? We can calculate how fast we're going, distance divided by time, and we can relate it to the planet being orbited using sort of that relationship that we started this section with. If we rearrange that, right, we get to this result right here. This is a mathematical statement of Kepler's third law, but we get something extra. We get this coefficient in front of it, right? And so this is how you could figure out, for example, the mass of the sun. If we know how long it takes the Earth to orbit, and we know how far away the Earth is, we can now calculate how massive the sun is, and thus we're there at all, without like going to the sun and trying to weigh it. This is how, for example, masses of planets that are very far off, extrasolar planets, are determined. This is how masses of galaxies are determined, by looking how the mass rotates around the center. Kepler's third law is basically how you get any information about mass about the universe in some form or another. Okay, and so again, this table can be very useful. It proves that data as well. Visible slides again. And so that's really where Kepler's third law comes from, right? There's a mathematical proof using Newton's laws that shows that must be true. So here's an example then of using that. We have a period for an extrasolar planet, and we have the distance that we orbit at, and you want to find the mass of that star that's being orbited. Okay? So this is just using Kepler's third law. One thing that's very important to note, Kepler's third law is not on the AP sheet because all it is using like 5 different pieces that are. It might be worth memorizing it because it's a lot of work to rederive, but if you have to use it on a free response, you have to rederive it. Here we're just going to take it as a given, right? We're going to start with Kepler's third law and rearrange it, and all we do is we plug in the values. Notice, right, we have to work in SI units, convert to seconds. We look up the radius of Jupiter, and we plug in. And so we end up getting that it's a very large number of kilograms, which is about 13 times the mass of our sun, or that's the unit called solar masses. Okay, so Kepler's third law can also be used to sort of figure out relationships between orbital times, right, even if not ever calculated. So if we know that t squared is proportional to r cubed, that is the same as saying r to the 3/2 is proportional to the period, right? Take the square root of both sides. So for planet A, we have capital R to the 3/2. For planet B, we have 4r quantity to the 3/2. Well, 4 square root is 2, cube 2 is 8, so this is 8r to the 3/2. And so because we made the radius side 8 times bigger, we have to make, right, the period side 8 times bigger. And so we have 8 times 20, which is 160 days. Right? I never actually even needed to calculate the mass of the planet. Just Kepler's third law can give me the relationship. So that one deals with energy. Kepler's second law is a momentum concept. Right? This statement that was really tough to describe is actually a statement of conservation of momentum. And I'm going to show this on the next slides. But it turns out that the area can be related to the angular momentum, L. And that must be a constant, right? This system, right, is isolated. So that means the angular momentum cannot change no matter what type of orbit we travel in, right? So here's how that works, right? And this is a proof that doesn't require it to be a circular orbit. So we're some distance r from the sun, we're moving some velocity v. In some very small time interval, we move a distance v delta t. If delta t is very small, then our motion is basically triangular. We aren't going through a curved arc length because delta t is so tiny, and obviously that means that we're really talking about a differential dt here. So we can calculate the area then that is sort of swept out, right? Going back to this picture, right? Like if we travel a distance like that, we can calculate the area that's swept out by calculating the area of a triangle, assuming that the time is very, very, very tiny, right? 1/2 times base times height. So the height is r, right? That's not changing in the tiny time interval. The base is how far do we travel, right? And this sine beta comes in because if I go back to this picture, right, notice that we're not going the exact direction of the velocity, right? We only go like a little bit, like a fraction of it. So we can rearrange that and multiply by m over m, right? And so we're left with the area is this right here. Now, Kepler's second law describes about the rate. So we divide by both sides by delta t, right? This is the rate of area. And you should see something very nice here, right? The stuff that I'm boxing, mv, that's p, right? R, and then sine. So this is R cross P. That is what we defined as L, right? And so that is a constant, and so therefore Kepler's second law is true. So here's why this is really handy. If Kepler's second law is true, we can tell something, we can very quickly relate how fast we're moving somewhere and at some position, some other position, right? This is an elliptical orbit. At point B, we're very far away. At point A, we're very close. If Kepler's second law is true, we have to move very fast here and very slow there, which is also a statement of conservation of momentum. So VA has to be bigger than VB. You can think about this, you can actually prove that you have to move faster at A through conservation of energy as well, right? We're closer to Earth's surface at point A, so that means we need a more negative gravitational potential energy and therefore a more positive kinetic energy, therefore faster. But it's easier to calculate using conservation of angular momentum. One last comment then about orbital energetics, right? Because there's a relationship between V and R, there's a relationship between the kinetic energy, which is usually only dependent on V, and the position, which is usually what we talk about for potential energy, right? I just plugged that in. But this is actually very familiar, right? UG is negative GMM over R. So the kinetic energy is always in a circular orbit, negative 1/2 of the potential energy. And so that means our total mechanical energy is always, first of all, negative, and second of all, 1/2 of what you would calculate as the potential energy. You never need to actually calculate the kinetic energy to find the total energy in an orbit. If you don't have this relationship, you can't have a circular orbit, period. So this is kind of just a graph that shows that. The handy thing from this is that because the total energy and the potential energy are very similar, just like divided by a factor of 2, you can kind of think about the total energy and the potential energy as the same sort of idea. And this tells you that to sort of move a satellite farther away takes energy added to the system. You have to like fire an engine or push an object or something like that. And that should again make sense from your everyday understanding of orbital energetics. So you can actually calculate that, right? The change in total energy, right, is the work, but the change in total energy is the same thing as doing the change in 1/2 of the potential energy, which is way faster to calculate, right? You don't need to calculate potential and kinetic separately because of this relationship. And so with that, you can calculate exactly how much energy it takes to move something to a higher orbit without worrying about how fast it's traveling at either one, right? The speed is sort of fixed because it's going at that it's in that orbit already. Okay. The other thing to note then is sort of the process of how, right? If you want to change from a circular orbit of one radius to a circular orbit of another, you can't just do it through one step. What you need to do is actually fire your rocket engines twice. Once right here changes your circular orbit to an elliptical orbit. And then the second one right here changes the elliptical orbit back into a circular one, right? This process, this whole process right here could be a whole class by itself, describing sort of orbital energetics and how to talk about sort of like the process by which you can perform these sort of mathematical goals. If you do have free time over break, a really cool thing to do is there's a game called Kerbal Space Program, which is actually very physics accurate about building and designing rockets to explore moons, basically, of a fictional solar system. So if you have time, play around with that. It really will help you sort of think about conservation of energy and sort of the process by which this happens, but it's really just a bonus thing. If you have Steam, you can get that Kerbal Space Program. The important bit is really that you recognize sort of how you need to apply the force as well. Notice that it's also fired, it's tangential, right? You don't fire your rocket to push you away. You try to speed up by firing your rocket in the direction you're already moving to give yourself more kinetic energy. So that's really it for the gravitational stuff. It's important to think about gravity both as forces and sort of energy and momentum separately, which is why this is split into those two parts.